Okay, let me introduce a couple of more different normed spaces. For P is between 1 and for any P which is more than or equal to 1 and which is finite, we have mentioned L sub C upper P at R, which was the collection of real valued functions which are continuous and P's power integrable, which means the improper integration from negative infinity to positive infinity on the whole real number line. The P's power of that function f is some finite number. That means the function f is P's power integrable. And on this set here, we define the norm of any function in this set, okay? It was defined by 1 over P's power of integration of P's power of the function f. And that was what we have studied the last time, and then we didn't do its detailed proof, but I introduced two different lemmas to prove that this set with this function is a normed space. So to prove that this is a normed space, as I have introduced, we must use Young's inequality, which is the first lemma, and Holder's inequality, which is the second lemma. Well, actually, the first two parts of the definition of the normed space are easy, but the third part is very much challenging. To prove the third part of the definition of the normed space, we must use those two lemmas I have introduced. And then the third part of that, the definition of the normed space on this set over here is called what? Called the Minkowski's inequality, which is very much challenging. Right? Yeah. So, and some of you did make a copy, photocopies of the proof, and then you can read it out. Even if it's long, that's not very much, very much hard. That's not very much challenging, but that's quite long. Yeah, that's why we have skipped its proof here. How about if P is equal to infinity then? Then I introduce another normed space, which is L sub C upper infinity at R, which is again the collection of all real variable functions which are continuous and bounded, which means supremum of absolute value of those all function values of f on the whole real number line R must be some finite number, which means the function f is bounded on the whole real number line. On this set here, we define a norm of any function f in this set is defined by the supremum number on the whole real number line R. Then you can easily justify that what? This set and this norm we have just defined here makes a normed space. Yeah, you can easily check the three conditions of the definition of the normed space on this set. You already know the supremum properties we have studied in real analysis last year, and then you can apply all those together to check out all three conditions for the definition of the normed space on this set. And then, if we let distance between the two functions f and g on this set to be what? Difference between norm of their difference. We have just defined, which is same as supremum of absolute value of their difference on the whole real number line R. Then the set over here with the d distance function makes a metric space. That's a metric space then. That's a metric space. That's a metric. That's the metric induced from the norm here we have defined. Okay? The distance between two functions is defined by the norm of their difference. Norm of their difference. Then how do we rewrite the norm of their difference? That's the supremum of their difference. Okay? On the whole real number line. And then because this defines a norm on this set. Okay? If we define the d distance function using that norm, which is the norm of the difference of functions, and then what? That automatically makes a metric space. Metric space, as you have already justified at the very beginning of the semester. Right? Well, what was the metric we have defined on this here when p is finite? P was finite. What was the metric d we have defined on when the p was finite last time? Yeah, distance between the two functions f and g in LP is defined by, again, what? Norm of their difference. Okay? Norm of their difference we have just defined, which is same as what? 1 over pth power of integration on the whole real number line pth power of the difference of two functions f and g. Then LP set with D we have just defined there makes a metric space. Yeah, if you have any normed space, and then that defines a metric, right? As you have already justified at the beginning of the semester. Okay? Yeah. Let me also introduce the normed space that looks like for p is some finite number which is more than or equal to 1. Little l sub p, little l upper p at the set of all natural numbers is defined by what? You know, when we had L sub C, L sub LP at R, that was the collection of what? Collection of functions defined on the domain space R. So if we have little l p at n, the set of natural numbers, then naturally that must be the collection of what? Collection of functions defined on the whole natural numbers, right? Then what is a function defined on the whole natural number? What do you call that? Let's say sequence, right? Sequence. So little LPN is the collection of all sequences okay. Little LPN is the collection of all sequences on the real number lines such that all a sub n's are real numbers for all natural number index n. And one more condition. Sum of their piece powers is finite. Yeah, that is the definition of little LP space, which is the collection of all real sequences. Collection of all real sequences such that its piece power is summable, which means what? Summation of the piece powers of the terms is some finite number. You know. You can compare little LP and large LP. Pretty close to each other, right? Yeah. On the large LP, what? That was the collection of functions on the whole real number line R. In little LP, that is the collection of all functions on the set of all natural numbers, which means the collection of sequences, right? Yeah, sequences. In capital LP here, then what? We have this piece integrable condition here. Piece power integrable condition. Then what is the corresponding condition for little LP, for the sequences? Integration over here must be changed to what? Summation in the discrete sense, right? So that means, yeah, that's a collection of sequences, which is piece power summable. Piece power summable. That's what that means. They are corresponding to each other. And then on this set here, let's let the norm of the sequence in this set to be again 1 over piece power of this sum. That's exactly the same pattern as we had in the capital LP, right? 1 over piece power of the summation of piece power of the terms of the sequence. Then on the little LP set with the norm defined. Okay? On the little LP set, the norm defined over here. Okay? We have just defined, makes a normed space. So we can immediately write out the induced metric from this norm, right? So let's let a distance between two sequences A and B on this LP set be the norm of their difference, where A and B both are sequences in little LP. And then let's let distance between the two sequences be the norm of their difference we have just defined, which is same as what? How do we write it? Norm of the difference of two sequences, which is same as what? Same as 1 over piece power of sum of piece power of their difference, term by term. Then of course, this distance function D makes a metric space on little LP. So the justification of, okay, you can check out, three conditions for the definition of the normed space on this set. That takes time, but you can check it out for yourself. Yes. And then this normed space induces a metric space. Okay. That's always happened. That's always happened. Yeah. Finally, how about if P is infinity? Little l infinity, what does that stand for? Why don't you look at capital L infinity? That will be corresponding to little l infinity. That's my last example of normed space I introduced here. Little l infinity at the set of all natural numbers n is defined by what? Defined by a collection of what? Collection of all functions defined on n, which is what? Again, which is what? Which is a collection of the sequences on the real number line. And what is the corresponding condition to this here, boundedness? Supremum of each term must be finite, which means that's a bounded sequence. Okay, that's a bounded sequence. Supremum of absolute value of a sub n on the whole domain set, natural number must be some finite number, which means that's a collection of bounded sequence. That's a collection of bounded sequence. Bounded sequences on the real number line. That's what that means. Then what is the norm defined on this little l infinity? So let's let norm of the sequence little a in this l infinity be the supremum number. Supremum of absolute value of the terms of the sequence on the whole domain set natural numbers. Then this norm makes a normed space on this L infinite set. Little L infinity at n with the norm we have just defined there makes a normed space, which you can easily check. You can easily check the three conditions to be normed space on this set L infinity using the supremum properties and so on. You can easily check it out. So once we have a normed space, we can automatically induce a metric space, right? So let's let D between the two sequences A and B on this L infinity set to be norm of their difference. Which means norm of their difference is what? Norm of their A minus B must be supremum of, okay, difference of the terms of the two sequences. Then this is the induced metric from the norm. So this D metric makes a metric space on this little L infinity set. And that's automatically induced once we have any normed space on the same set. Yeah. So then we will do more, details about capital L infinity and little L infinity next semester, in the major theories, major theory, okay, which is they are very crucial on the major theory space, major theory, study, which we will do details. We will do more details about. Any questions? Any comments? I just briefly introduced different examples of normed space and induced metric spaces. Okay, then let's change the topic. Let's change topics. Let's talk about the separable topological space. What do you mean by separable? We have a topological space in general, which is the general case of metric space. And then what do you mean by the topological space or a metric space is separable? That's what you want to study roughly here. Let's start from a definition. A set A in X where X is a topological space is dense. Okay, is dense in the topological space X. Yeah, we want to define what do we mean by denseness of a subset A on the topological space. Yeah, we have the whole topological X space X with topology on it, and then we have some subset A on it, and then we say that the subset A on the whole topological space is dense, is a dense subset of the topological space if the following is satisfied. If its closure covers the whole topological space X. Yeah, we say that a subset A on the topological space X is a dense subset if its closure, if you take its closure, that covers the whole topological space X. You know. So in other words, that means what? That means, you know, the subset A is large enough to cover whole topological space. So if you look at only elements in the subset A, and then what? We can characterize anything about the whole topological space because its closure covers the whole, right? You know, which means the subset A is almost all. That's almost all for the whole topological space. That's what that means. And then, you know, what is the equivalent condition for the denseness in a metric space? So let's let X with D be a metric space, which is a special case of topological space. Then, what is the equivalent condition that the subset A is dense? Yeah, what is an equivalent condition for what? The subset A is dense. That's a metric space, so that it has a metric. So then, yeah, you know how to write it out, right? You know, that means, yeah, these two sets are equal to each other. So that means for all X in X, X must be in a closure. Equivalently, first of all, of course, it must be, right? You know. Every element in X must be in a closure. That's what that means. Then how do we rewrite it? Write it out equivalently using metric. That's a metric space, not a general topological space. So that has a metric. So then how do we write it out using the metric on the metric space? Every element in the whole metric space is in a closure. So how do you write it out? So for all element little x in capital X, that element little x must be in a closure. Then what does that mean equivalently? X is in a closure. What does that mean equivalently in the metric space? There exists some epsilon neighborhood, okay? Epsilon neighborhood around X, such that open board, okay? Epsilon neighborhood around X, okay? Epsilon neighborhood around X must contain some element in A, which means what? The intersection of that epsilon neighborhood around X and the subset A must be non-empty. Non-empty. That's the equivalent condition for the denseness. Every element in cap X must be in a closure. So then that's equivalently what? Every element in X must have must satisfy the condition here. Okay? Little x is in a closure. How do we write it out? That's in a closure. That means what? There must exist some epsilon neighborhood around X that contains some element capital A, which means the intersection of that epsilon neighborhood and the subset A must be non-empty. Some element must be in both, right? Yeah. By the definition of the closure we have studied previously. Yeah, that element is in the closure of this set means what? Equivalently, there is some epsilon neighborhood around it which contains some element in A. That's what that means. You already have a trivial dense set on the whole real number line R, which is what? Set of all rational numbers. Right? You already know what? The set of all rational numbers is dense in the whole real number line, right? You know, by denseness of rational numbers on the real number line, right? Yeah. Yeah. Well, let me describe another definition. Then what do you mean by separable topological space? We say that a topological space X is separable separable. What do you mean by a topological space is separable? We say that a topological space X is separable if simply there is a countable dense subset of X. That's the simple definition of a separable topological space. In other words, that means there exists a countable subset A in the whole topological space X, such that its closure is the whole topological space. That's what that means equivalently. So this is stronger condition here, stronger topological space. That means the whole topological space is curved by what? Only countable subset. That's what that means. Here's the whole topological space X with its topology on it, and then only countably many elements curves the whole topological space. That's what that means. only countable subset capital A covers the whole topological space. The closure of some countable subset is the whole topological space. That's what that means. So that's a very strong condition. Then then I would say that the whole topological space is pretty close to what? The only countable subset, capital A. Pretty close to each other. So that means, if we study only this countable subset, then what? That's almost all for the study of what? The whole topological space. That's what that means. So that's a very strong condition. That's a very strong topological space. For example, as you already know, the whole real number line R with the usual metric, which is the absolute value, okay, is a separable topological space, separable metric space. You already know the closure of collection of all rational numbers is the whole real number line on that absolute metric. Okay, over here, Q is the collection of all rational numbers. And then the collection of all rational numbers, which is a countable subset, right? The closure of this countable subset Q covers the whole real number line. So, yeah. So the whole real number line R with that absolute metric, okay, the usual metric, is a separable metric space. That's a separable topological space. But if we change the metric, then what? Then may not be separable. It totally depends on how the metric looks like. Right? Yeah. Secondly, how about the n-dimensional Euclidean space with the usual metric on? You know the usual metric on, right? We have defined. That's also a separable metric space. Then what is your idea of a countable then subset on the whole n-dimensional Euclidean space then? Let's let Q to the n be the collection of n-tupled rational numbers. You understand the structure of this set Q to the n. Yeah, that's the collection of n-dimensional vectors such that each component of the vector is a rational number. The rational component is what? N-dimensional vector. That's the collection Q to the n. And then what? We can easily justify that what? Yeah, that's of course a countable set, right? So each quantum is countable, so what? That whole Q to the n is a countable set. And you can easily verify that the closure of this countable set Q to the n covers the whole n-dimensional Euclidean space. How do we claim the closure of this countable set covers the whole n-dimensional Euclidean space? We work component-wise. We work component-wise and combine them together afterwards. How do we work component-wise first? We want to claim the closure of this countable set Q to the n is same as the whole n-dimensional Euclidean space. So for that purpose, let's take an arbitrary element in n-dimensional Euclidean space. So let's let x be any n-dimensional vector. And let's let epsilon be an arbitrary positive number. And then let's work component-wise. Okay? So we can pick the rational numbers r sub 1, r sub 2, up to r sub n, rational numbers, such that difference between first, second, and up to nth component are less than epsilon divided by square root of n, where k is any index number from 1 to n. So x sub 1 minus r sub 1 is less than this number. Same thing for all other differences. x2 minus r sub 2 is less than that. Yeah. Okay? You know. So we work component-wise and then combine all together, which is easy for you. Then let's let r be all this here, the rational numbers we have picked up. Then this vector r is in the q to the power n. Okay? Q to the power n. Then we want to claim the difference between x and r. Difference between those two n-dimensional vectors is less than epsilon, which is easy for you, right? We worked component-wise. We estimated component-wise first, and then let's combine all together for our goal. Our goal is to justify that what? Distance between, okay? Those two n-dimensional vectors. Yeah, the original one, x, is in the arbitrary n-dimensional vector. But the second one, r, is the rational component in n-dimensional vector. So we want to claim their distance is less than epsilon. Yeah. Distance d between those two vectors, x and r, must be same as by the definition of the metric here in the n-dimensional space. That is the square root of half power, square root of sum of squares of components differences, x of k minus r sub k. Yeah, that's the definition of D metric on the n-dimensional Euclidean space. Then which must be less than what? Less than, we already worked component-wise, less than half power of sum of each component difference is less than that number. So its square must be epsilon squared divided by n. That's what's happening. Which is same as epsilon squared is a constant. We can take it outside of the sum, and then epsilon squared to the power 1/2 makes epsilon, which is outside of the bracket, and then what's only left over inside? The only leftover inside is that's only left over. And epsilon times half power of add 1 over n times, add 1 over n times, that must be positive 1. So we end up with epsilon. be empty. So we have claimed that no matter what n-dimensional vector, arbitrary n-dimensional vector we choose, depending on that, and no matter what n-dimensional vector we have chosen, and no matter what positive number epsilon we have chosen, depending on that, there is some element in Q to the n such that the distance between the original n-dimensional vector and the other vector in Q to the n is less than epsilon. That was what we have claimed. So that stands for what? That stands for the closure of Q to the n covers the whole n-dimensional space. That's what we have claimed. Which means Q to the n is a countable dense subset of R to the n, n-dimensional Euclidean space. Which means R to the n with the metric in unit. The user metric is a very strong topological space, which is called a separable topological space. Separable metric space. Yeah, we need only countably many. Okay, we need only countably many elements to cover the whole uncountable set. That's countable, but this is uncountable, right? Yeah. But we need only countable set that covers the whole uncountable set. So that is a strong topological space, strong metric space, which is called a topological, separable metric space. Okay? Separable metric space. What is another example of a separable metric space? Little LP. Little LP is another example of separable metric spaces. Little LP. You imagine little LP. That will be a separable metric space. Then can you imagine a countable dense subset of little LP in your mind? How should it look intuitively? Little LP with that little LP norm, little LP metric we have defined is another example of separable metric spaces. Which means there is some countable dense subset of little LP. Then do you have any idea about the structure of what? Structure of a countable dense subset of little LP? For any natural number k, let's let little a sub k be the collection of this sequence, where the first k components are arbitrary rational numbers, but all other components are zeros. You understand the structure of this set, A sub k. Yeah, that's the collection of this sequence, such that the first k components are arbitrary rational numbers, but all others after that are zeros. That's how this capital A sub k looks like. That's how we define capital A sub k here. That's a subset of little LP, of course it is, right? Because what? If you take the piece power sum, then that must be finite, because only finitely many terms are alive here, right? Of the sequence is alive. So that's definitely what? a subset of little LP, which is, of course, countable, because the rational set of rational numbers is countable. But I don't think this is good enough to cover the whole LP. We have infinitely many A sub k's depending on the natural number index k, right? So our next step is to take all their unions. So let's let capital A be all of their unions. Where k is from 1 to infinity. Then you already know the union of countably many union of countable sets is still countable. You have, I believe you already have that experience on the set theory. You know, we have each A sub k is countable. And then we take the countable union, k is from 1 to infinity. We take the countable union of countable sets. Then what? That union must be also countable. Countable. And then we want to claim this countable set we have constructed here covers the whole little LP space. In other words, the closure of this countable set A covers the whole little LP. Yeah, that's what we want to claim. That's what we want to claim. So we will conclude, okay, we will conclude little LP is a what? Is a separable metric space. It has a countable dense subset, capital A, we have constructed here. Then we will start from the justification of this next time, next week. Have a nice Thanksgiving break. Yeah. So the separable metric space is a very strong metric space that has a lot of nice properties. We will see it. Okay, we will see.